Hello everyone, welcome to a new lecture in the series of data-driven model predictive control. In this lecture, we will be reviewing some basic concepts from conventional linear MPC, where we discuss the output and state-based linear MPC formulations. Here is the overview of this lecture. We will be starting with output-based linear MPC and its formulation. Then we move on to state-based LMPC. In output-based LMPC, we will be using the output information or output feedback for computing the MPC control law. The linear MPC is based on the discrete time linear system, which can be represented as in equation number 1, where xk is the state vector, uk is the control input vector, and yk is the output vector. And the A, B, C are the system metrics, input metrics, and output metrics respectively. And in MPC, we normally uses the predicted sequences, which can be represented as in equation number 2, where capital Xk plus 1 denotes the predicted state sequence. It contains the predicted value of the states from the time instant k plus 1 till k plus n, where this xk plus 1 given k denotes the predicted state at a time instant k plus 1 computed at a time instant k. And similarly, yk plus 1 given k denotes the predicted output at a time instant k plus 1 computed at a time instant k, and so on. In the case of MPC, the cost function will be normally defined using this predicted state sequence, predicted output sequence, and control input sequence. Here, this capital N denotes the prediction horizon, which is basically the number of future instants we will predict the sequence. In the case of output-based linear MPC, the cost function can be defined as in equation number 3, which consists of a quadratic sum of the output prediction error and also the control input error, where this QY denotes the output weighting matrix and RU denotes the input weighting matrix, and YR and UR denotes the output and input references. So here we will be summing this quadratic function of the prediction error for n time instance, where n is the prediction horizon. Then in the case of MPC, given the current input information, the objective is to compute the optimal control sequence UK, which minimizes the cost JY over the prediction horizon subjected to these constraints. So where the predicted state sequence should satisfy this system equation or the state equation, which will be an equality constraint in the optimization problem. And these are basically the output constraint and input constraint, which can be defined using linear inequalities. Now, from the previous slide, we have the cost function for output-based LMPC as in equation 5. And by defining the block diagonal matrices capital QY, which contains all these individual weighting matrices as its diagonal element, and similarly the capital RU, which contains all the input weighting matrices as its diagonal, and this YR contains all the output reference value as its column elements, and also UR contains the input reference for all the n instance. We can represent the cost function in equation 5 as in equation 7, and if you expand this term, we will be getting it as a summation of n terms, and similarly for the control input term. From the state equation, we have xk plus 1 equal to axk plus buk, which gives the predicted output yk plus 1 as c into xk plus 1, which will be ca xk plus cb uk. And now by using this, we can compute the predicted output sequence as in equation 9, where we have yk plus 1 given k will be equal to ca xk given k plus cb uk given k. And by recursively using this equation, we can find all the predicted output over the prediction horizon. This will gives us the predicted output sequence or capital yk plus 1, which can be represented as ay xk given k plus by uk. And using this expression, we can rewrite the MPC optimization problem as in equation 10. This equation is based on the state space model of the system, and it captures the system dynamics. And here we replace this predicted output sequence or yk plus 1 with this expression, and which will modify the cost function as given here. And similarly in the constraint also, we can replace this capital yk plus 1 with this term, and this will modify the optimization problem as in equation 10. Now this optimization problem can be reformulated as a standard quadratic programming problem, and for that we can expand and rearrange these terms, which will be coming up next. So here we have expanded the cost function from the previous slide, and we can also discard the term that does not depend on UK, which are shown in this red color. Then we can rearrange these terms as in equation 12, which gives us the cost function jy as UK transpose hy UK plus UK transpose qy, where hy will be this matrix and qy will be this vector. Similarly, we can also represent the output and input constraints using linear inequalities, where we have the individual constraints as fi yk plus 1 given k less than or equal to gy, fi yk plus 2 given k less than or equal to gy, and so on. And this block diagonal matrix capital Fi contains each of these individual matrices used for defining the constraint. And this will give us the output constraint as fi yk plus 1 less than or equal to gy. And similarly for input, we have fu uk less than or equal to gu. And here also for capital yk plus 1, we can substitute the system equation, which will gives us this expression. Here we can include only the terms with capital UK in the left hand side and take all other terms to the right hand side, which will give us the final equation for the constraint as FIU UK less than or equal to GYU, which is in the form of a linear inequality constraint. We obtained the cost function for the MPC optimization problem as a quadratic function and the constraint as a linear inequality constraint, which will give us the optimization problem for output-based LMPC as in equation 16, which is in the form of a standard QP, where we have a quadratic cost function and a linear inequality constraint. In MPC, we will solve this optimization problem at each time instant to find the optimal control in sequence capital UK, from which the first element is applied to the system. Next, we move on to state-based LMPC. And in the case of state-based LMPC, the only difference is that here we will be using state feedback information for computing the MPC control law. So in the case of state-based LMPC, the cost function will contain a quadratic sum of the state prediction error terms and also the control error terms, where this QX is the state weighting matrix and RU is the control input weighting matrix. Then in the state-based LMPC, the problem is to compute the optimal control input sequence UK, which minimizes this cost function subjected to these constraints, where we have the state equation as the equality constraint, and this inequality constraint will be defined using the state and input constraints. Now, similar to the output-based LMPC, defining these block diagonal matrices capital QX, capital RU, XR, and UR, we can represent this cost function for the state-based LMPC as in equation number 22. Then using the state equation, we can compute each element this predicted state sequence, where xk plus 1 given k equal to a into xk given k plus b uk given k. And by recursively applying this equation, we get all the future states over the prediction horizon. And this matrix we can compactly represent as capital AX, and this matrix as BX, which gives us capital xk plus 1 equal to AX xk given k plus BX uk. This can be considered as the predicted state sequence equation, which we can substitute in the MPC cost function and rearrange the terms, which gives us the cost Jx equal to UK transpose Hx UK plus UK transpose Qx. And similar to the output-based LMPC, we can represent the state and input constraints as a linear inequality, which is in the form of Fxu into UK less than or equal to Gxu. Now, by using this cost function and this constraint, we can define the optimization problem for state-based LMPC as in equation 26, which is in the form of a standard quadratic programming problem. Similar to the output-based LMPC, this optimization problem can also be solved using any solvers for QP. And then the first element of the control input sequence will be applied to the system. The numerical examples for state-based LMPC was given in one of the earlier lecture series on MPC, for which the link is given in the description. In this lecture, we have considered the conventional LMPC scheme, where we assume the model parameters or the ABC matrices in the state space model are known, using which we can basically compute all these parameters in the MPC optimization problem. In the next lecture onwards, we will be moving on to data-driven linear MPC, where we consider the system parameters or the ABC matrices are unknown, and therefore we have to identify these parameters from the data and then use it in the MPC optimization problem. That leads us to the end of this lecture. Thanks for watching.